specifically, this is section 4.2, graphs of polynomial functions. Zeros, turning points, and graphs. Zeros. Okay, we already know what zeros are, so recall. A number x equals z is called a zero of a function f and only if f of z equals 0. It basically comes down to trying to factor the polynomial. So, some examples. Let's find the zeros of each function. F of x equals 19. 19 can never be 0. Okay, there is no x, so f has no zeros. As a little note, the degree of this polynomial function is 0 because there is no x, and there are 0 zeros. Number 2, g of x equal to 3x plus 9, a nice linear function. So we set 3x plus 9 equals 0. Okay, subtract 9. So we have 3x equals negative 9, divide by 3, and x is negative 3. So x equals negative 3 as our 0. Now, the note, it's degree 1, and there is 1 0. Number 3, h of x is equal to x squared minus 7x minus 8. A nice quadratic function. So we have x squared minus 7x minus 8 equals 0. Okay, we want numbers that multiply to be minus 8 and add up to be minus 7. It's got to be 1 and 8, and the bigger has the minus sign. So I have x minus 8, x plus 1 equals 0. X minus 8 gives me 8, and x plus 1 gives me negative 1. So there are my zeros, 8 and negative 1. And again, notice the degree is 2, and there are 2 zeros. Must be a pattern going on here. Number 4, I have k of x equals 2x cubed plus 4x squared minus 6x. Okay, we're going to set the polynomial equal to 0. So I've got 2x cubed plus 4x squared minus 6x equals 0. Okay, I can factor out 2x from everybody. So I'll have 2x times x squared plus 2x minus 3. Okay, now I need numbers that multiply to be minus 3 and add up to be 2. It's got to be 3 and 1, and the bigger gets the plus sign. We'll have 2x times x plus 3 times x minus 1 equals 0. And then we set each factor equals 0. Okay, 2x gives us 0. X plus 3 gives us the negative 3. And x minus 1 gives us 1. 3 zeros, and the degree is 3. The pattern appears to be holding. Number 5. I have p of x equals x squared plus 10x plus 25. Okay, we're back to a degree 2. So we set the function equal to 0. X squared plus 10x plus 25 equals 0. Okay, multiply by 25 and add to be 10. It's 5 and 5. So I have x plus 5 times x plus 5 equals 0. All I get is x equals negative 5. It does have multiplicity too, but I only have 1 0. But the degree was 2. So the degree is 2, but only 1 0. But notice if I count the multiplicity, it'll match up. This is what really happens. Fact. A polynomial function of degree n greater than or equal to 1 had at most n distinct real zeros. Remember, the zeros also correspond to the x values of the x-intercepts. So the degree kind of tells you the greatest number of times it can cross the x-axis. So this means that a polynomial function of degree n greater than 1 will have at most n x-intercepts. Just remember, the zeros correspond to the x-coordinates of the x-intercepts. So if the polynomial function has degree n greater than or equal to 1, you have at most n x-intercepts. Turning points. Okay, turning points. Definition. A turning point is a point on a graph where the graph changes from increasing to decreasing or decreasing to increase. In other words, it turns. Okay, that's what it amounts to. It turns. So it changes from increasing to decreasing or decreasing to increasing. A picture of this. This is a turning point. I'm going from increasing to decrease. And this is a turning point. I'm going from decrease to increase. Notice it amounts to maxima and minima. So the turning points are the max and min points. We're going to set up a relationship between the degree, the graph, and the number of turning points. Okay, see if we can discover a pattern. So if it's degree 1, it's a line. Okay, a line doesn't have any turning points. It's always going uphill, always going downhill, or else it's a horizontal line like that one. Okay, degree 2, remember that's the parabola. Right side up, upside down. So degree 2, it's a parabola. There's one turning point. Remember, that turning point is the vertex. Okay, on the parabola, the turning point is the vertex of the parabola. Remember, degree 3, we're kind of S-shaped, so I could have two turning points. But if you remember when we graphed one of our basic functions, y equal x cubed, it didn't have any turning points. So degree 4, a w, an m, a u, or a u upside down. Notice the w and the m have three turning points, but the u or the u upside down only has one. Again, remember, for the S shape, there could be 0. But notice the number of turning points isn't any bigger than degree, and it appears to be that it's usually one less than degree. Okay, fact. A polynomial function of degree n has at most n minus 1 turning points. Okay, at most n minus 1 turning points. So remember, the degree is n, and n minus 1 is the greatest number of turning points. Let's try some examples. Determine the smallest possible degree for each polynomial function whose graph is given. Okay, so we're going to draw the graph and then figure out the smallest possible degree. Okay, so here's my graph, this thing. Okay. So our solution, we're going to count the turning points. Okay, so I've got 1, 2, 3. Remember, the turning points is n minus 1. So n minus 1 is 3. Add 1, you get n is 4. So the smallest possible degree is 4. Now if you notice, both ends are up, so it has to be even degree. So degree could be 4, 6, 8, and so forth. So remember, if both ends are in the same direction, that's even. Number 2, there's my graph. So I count my turning points. Looks like 1, 2. So remember, that's n minus 1. n minus 1 is equal to 2. Okay, add 1, I get n is 3. So the smallest possible degree is degree 3. Remember, it has to be odd degree because the ends are in opposite directions. So it could be degree 3, 5, 7, and so on. But the smallest possible degree is 3. Some graphs. We will try to get some idea of the general shape and behavior of the graphs. Your graphing calculator can graph any polynomial function. And typically you can do it quite well, even if the polynomial is given to you in factored form. You just have to enter it correctly. So some examples. We're going to graph the following. Okay, I've got f of x equal x to the 4th minus 4x squared. Okay, if we want to let our graphing calculator graph it, so let's just take it out here. Okay, it's the graphing right over here. Y equal x to the 4th. Okay, get out of the exponent. Minus 4x squared, and just graph away. So I'm getting what really looks like a W. Remember, 4th degree are either W's, M's, U's, or U upside down. So let's see if we can get the same thing when we do it by hand. Okay, the idea is, I'm going to try to graph it if I can, but it is quartic. Both ends are up. Remember, plug in -1 for x into the leading term and plug in 1 into the leading term. Okay, we can factor f of x. Right, I can factor out an x squared. It'll give me x squared times x squared minus 4. I have a difference of squares. I can factor it. So I have x squared times x minus 2 times x plus 2. Remember, I'm going to be able to get the zeros, which will give me the x-intercepts. So x squared gives me 0, x minus 2 gives me 2, and x plus 2 gives me -2. So it's tangent to the x-axis at x equals 0. Even degree, even exponent. It crosses the x-axis at x equal 2 and x equal -1. Right? Odd multiplicity, even multiplicity. So I'm going to make a little table of values. Okay, now I already know that both ends are up. What I'm going to do is I'm going to plot values of x that are halfway between consecutive x-intercepts. So halfway between 0 and 2 is 1. So I plug in 1, I have 1 minus 4, which gives me the -3. Okay, halfway between -2 and 0 would be -1. Okay, -1 to the 4th is also 1. -1 squared is also 1. So I still have 1 minus 4, which is still -3. And remember, I've got my x-intercepts, 0, 2, and -2, and I've got these points. So there's my x-intercepts. and here's where I did the 1 and the negative 1. And this should look like what we graphed on our graphing calculator. Now again, since it is a function, and in D2L the graphs are multiple choice, I would just go ahead and look at what the graph from the graphing calculator would look like. Let's try another one. I've got g of x is x minus 2 squared times x plus 1. Now, if we were to multiply it out, I'd have an x squared times an x. It is cubic. Okay? So it's going to look like an s. So the leading term is x cubed, because if you do x squared times x, I get x cubed. If you plug in negative 1 and cube it, you get negative 1. Left end is down. If you plug in 1 and cube it, you get positive 1. Right end is up. So left end down, right end up. Okay, my zeros, which is going to correspond to my x-intercepts. From x minus 2, I get 2, that is multiplicity 2, so it's going to be tangent at the x-axis at x equal 2. From x plus 1, I get negative 1, that's odd multiplicity, so it's going to be crossing the x-axis at negative 1. So I make my little table of values. Okay, I'm going to pick 0, it's something between minus 1 and 2. If you plug in 0, 0 minus 2 squared times 0 plus 1. Okay, minus 2 squared is 4, 4 times 1 gives me 4. Then I plugged in 1. 1 plus 1 is 2. 1 minus 2 is negative 1. Negative 1 squared is 1. That's how I got the 2. And there's my graph. Okay, crossing at x equal negative 1. Tangent at x equal 2. 0, 4. And then there was my 1, 2. Now again, if we gave it to the graphing calculator, so if I take out the graphing calculator here, y equals, okay, remember I had x minus 2 squared times x plus 1, and let it graph. And does this graph look basically like that graph? Well, except for the color, yeah. Okay, I've got one more. This will be a fun one. X times x plus 2 times x minus 1 squared times x plus 3. Now notice if I multiply this out, I have x times x, which is x squared, times an x squared is x to the 4th times x. It's a 5th degree polynomial. It's a quintic. So my leading term is x to the 5th. Okay, if you plug in negative 1 to the 5th power is negative 1, left end down. 1 to the 5th power is positive, right end up. Okay, let's see, my zeros. I got 0, negative 2, and negative 3. Those all have multiplicity 1. It's crossing the x-axis at x equals 0, then at x equal negative 2, and at x equal negative 3. Those all have exponents of 1 as factors. The other 0 is x equal 1, and it's going to be tangent. Okay. Now again, I would like to plot x values that are halfway between consecutive pairs of x-intercepts. So I'm looking at my x and my h of x. Okay, now again, if you want to take the kind of the lazy way out again. So I've got my y equal. Okay, I've got x, open parenthesis, x plus 2, close, open, x minus 1, and that one's squared, open, x plus 3, close, whoops, lost my plus sign, plus 3, close, and then just graph away. So I get this kind of weird looking thing. Okay, let me quit that. Now, for my table of values, I plugged in 0. And you can see 0 times whatever is going to be 0, which we already knew from right there. Then I did the negative 2.5. That's halfway between negative 2 and negative 3. And again, in the calculator, remember how to do this? You go vars, y vars, function, so enter. It's in y1. Okay, open parenthesis, negative 2.5, close, close one. And you get the 7.6565. So that was the x value halfway between negative 2 and negative 3. Okay, and then if I go to the next one, halfway between 0 and negative 2 is negative 1. And again, we can verify that. Vars, y vars, enter, enter, open, -1, close. Okay, and I get -8. And let's see, so that was halfway between 0 and -2, and then I want halfway between 0 and 1, that would be 0.5. So vars, y vars, enter, enter, open, 0.5, close, enter. So I should be getting 1.09375, so just a smidge above 1. And then there's our graph. So again, remember we already graphed it here, so let's clear that nonsense out and graph. So, do they look alike? Sure do. Again, since they are functions, unless you specifically asked some of these other questions like what is the x-intercept, what are the zeros, what's the y-intercept, that type of stuff, I would just go ahead and let my graphing calculator do it. Remember, in D2L, they're multiple choice. You want something that you can tell whether or not it matches. Okay, smooth and continuous graphs. Okay, smooth and continuous. Let's do the smooth first. Okay, we're going to kind of give you the working definition. There is going to be a precise definition should you take calculus. So, definition. A graph is called smooth if and only if it has no sharp corners or points. I think the classic example of a function with a sharp corner or a point is the absolute value function, that v. And the absolute value function is not a polynomial. Illustrations. Okay, the following graph is not smooth. It has a sharp point at 0, 0. The graph is actually the graph of y by absolute value of x. The sharp point is called a node. So there's my sharp point. It's kind of like if you were traveling along in your car, you might have to really slow down to make that turn. Okay, the next graph is also not smooth. It has a sharp point at 0, 0. The graph is actually the graph of y equals x to the 2/3 power. The sharp point is called a cusp. Again, in calculus, you'll see the difference between them. So, again, if I were traveling along in my car, I'm coming down here, and if I had to make this turn, that would be a hard turn to make. So there's my sharp point. Okay, that's my sharp point. The next graph is smooth. The graph is actually the graph of y equals x squared. And there that is. Again, if you were traveling along in your car, you'll be able to make that turn without too much trouble. Fact. The graph of a polynomial function is smooth. So that means no sharp corners or points. So polynomial functions do not have any sharp corners or points. It's also sometimes stated this way. Except for linear functions, no part of the graph of a polynomial function is a straight line. Okay, but remember, that basically means no sharp corners or points. Okay, now what is continuous? So continuous graphs. Definition. A continuous graph is a graph that has no holes, breaks, or gaps in it. In other words, the graph is in one piece. Okay, that's going to be our definition for it. Should you go to calculus, you'll see it more precise. So basically, a continuous graph, the graph is in one piece. It's also stated you can draw it without lifting your pencil. Now notice, a continuous graph can have sharp corners or points. The three examples we just looked at, the two that had sharp corners or points and the third one that was smooth, they were all continuous. So note, we often say that you can draw a continuous graph without lifting your pencil. Fact. All polynomial functions are continuous. So if you put them together, all polynomial functions are smooth and continuous. So determine whether each of the following is the graph of a polynomial function. Okay, so you're just going to polynomial, not polynomial. First of all, verify that it is a function. If it's not even a function, it has no hopes of being a polynomial function. Here's our first one. I don't know about you, but I'm looking at this really sharp point at x equals 4. It's not a polynomial. Okay, it is a function, but it's not a polynomial function. So it's not smooth. That's what's wrong with it. It's not smooth. Again, the sharp point at x equals 4. Here's my second one. Okay, it is a function. It does pass the vertical line test. It is smooth. It is also in one piece, so it's continuous. It is a polynomial function. It's smooth and continuous. My third example. It is smooth, but it's in two pieces. It's not continuous, so it is not a polynomial function. And again, its problem was it was not continuous. It's in two pieces. Okay, the intermediate value theorem. Okay, it's sometimes for this section stated as the intermediate value theorem for polynomials. The basis of the intermediate value theorem is that a polynomial function cannot go from being positive to negative or negative to positive without being zero. Because remember, it's got to be in one piece. So if you're below the x-axis and then in the next instant you're above, you must have crossed the x-axis. So we now formally state the theorem. The intermediate value theorem for polynomials. Let f be a polynomial. If a and b are real numbers with a less than b that satisfy f of a and f of b have opposite signs, so one positive, one negative, then f of x has a 0 in the open interval a to b. That is, there exists a number c satisfying a is less than c is less than b with f of c equals 0. Again, this is stating very formally you cannot be on one side of the x-axis at one instant and on the opposite side in the next instant without having crossed the x-axis. Now note, the intermediate theorem is usually abbreviated as IVT, intermediate value theorem. Okay. So in order to verify the intermediate value theorem, you're going to be given the function, you're going to be given an interval, you evaluate f of a and f of b, and observe that they have opposite signs. That's all you care about is do they have opposite signs. Notice the theorem doesn't tell us how to find the 0. It just tells us that there is one. Let's try a few examples to see if we can make it a little bit clearer. So here's a picture of the IVT. Okay, here's x equal a, here's x equal b. Down here is f of a, it's negative. Up here is f of b, it's positive. So f of a and f of b have opposite signs. And notice, I cannot go from down here to up here without crossing the x-axis somewhere. Because if I did, that would say that the graph broke apart, which would mean it's not continuous. And remember, polynomial functions don't do that. Their graphs stay in one piece. So let's try some specific examples. Now sometimes these will be given as true false, that the intermediate value theorem does apply or the intermediate value theorem does not apply. So use the intermediate value theorem to show that f of x has a 0 in the given interval a, b, or show that the theorem does not apply. So here's our first one. F of x is 3x cubed minus 4x squared plus 16x minus 7, and my interval is from 0 to 1. About the easiest interval I can give you. Now what you're supposed to do is evaluate f of 0 and f of 1 and observe that they have opposite signs. So evaluate f of a and f of b. So f of a is going to be f of 0. So I'm going to have 3 times 0 cubed minus 4 times 0 squared plus 16 times 0 minus 7. So I've got 0, 0, 0 minus 7. So I get negative 7. So f of a is negative. That's what's important. F of a is negative. Now evaluate f of b. Okay, f of b is going to be f of 1. So f of 1 is going to be 3 times 1 cubed minus 4 times 1 squared plus 16 times 1 minus 7. So you got 3 minus 4 plus 16 minus 7. See, 3 minus 4 is negative 1. Negative 1 plus 16 is 15. 15 minus 7 is 8. F of a and f of b, so have opposite signs. One is positive and one is negative. So since f of 0 and f of 1 have opposite signs, the intermediate value theorem says somewhere between x equals 0 and x equals 1, f of x is going to be 0. So since f of 0 and f of 1 have opposite signs, the intermediate value theorem guarantees a 0 in the open interval from 0 to 1. Okay, it always does it for the open interval. Even if you're given a closed one, it always guarantees it for the open interval. Okay, that's all you have to do is observe that f of a and f of b have opposite signs. Number 2. F of x is 2x to the 4th minus 3x cubed plus 6x squared minus 7x plus 3. And the interval AB is negative 1 to 2. So again, evaluate f of a and f of b and see what happens. So f of a is going to be f of negative 1. I'm going to have 2 times negative 1 to the 4th, minus 3 times negative 1 cubed, plus 6 times negative 1 squared, minus 7 times negative 1 plus 3. So I've got 2 minus 3 times negative 1, plus 6 times 1, plus 7 plus 3. So that's going to be 2 plus 3 plus 6 plus 7 plus 3. Okay, that's 5, and 6 is 11, and 7 is 18. Looks like 21. So f of a is 21. f of negative 1 is equal to 21. And now let's try f of b, which is going to be f of 2. Let's see what happens there. So I have 2 times 2 to the 4th minus 3 times 2 cubed plus 6 times 2 squared minus 7 times 2 plus 3. Okay, 2 to the 4th is 16. So I have 2 times 16 minus 3 times 8 plus 6 times 4 minus 14 plus 3. Okay, I'm going to have 32 minus 24 plus 24 minus 14 plus 3. Okay, negative 24 plus 24 goes away. Okay, negative 14 plus 3 gives me negative 11. So it looks like I'm going to get 21. It's just an amazing coincidence. Okay, f of a and f of b are both positive. Okay, so because they're both positive, I don't know whether or not there's a 0 in the opening from minus 1 to 2. So since f of negative 1 and f of 2 have the same sign, the intermediate value theorem does not apply. Okay, if they have the same sign, there is no guarantee. There may be one, we don't know. But the intermediate value theorem does not apply. It doesn't guarantee one. Again, that's all you do. Evaluate f of a and f of b and observe the signs. If they have opposite signs, the intermediate value theorem does apply and there is a 0. If they have the same sign, the intermediate value theorem doesn't apply and you don't know if there's a 0. Let's take a look at one more. Okay, f of x is equal to 2x to the 4th minus 3x cubed minus 6x squared minus 7x plus 3. And my interval a, b is from 2 to 4. Okay, again, evaluate f of a and f of b and see what happens. Okay, f of a is going to be f of 2. So 2 times 2 to the 4th minus 3 times 2 cubed minus 6 times 2 squared minus 7 times 2 plus 3. So I have 2 times 16 minus 3 times 8 minus 6 times 4 minus 14 plus 3. So I have 32 minus 24 minus 24 minus 14 plus 3. And by the way, that should be a 2. It magically changed to a minus 1. So when I do the number crunching, I get negative 27. See, now it's back to 2. Now evaluate f of b. f of b is going to be f of 4. So 2 times 4 to the 4th minus 3 times 4 cubed minus 6 times 4 squared minus 7 times 4 plus 3. So I have 2 times 2, 56, minus 3 times 64, minus 6 times 16, minus 28 plus 3. So I have 512, minus 192, minus 96, minus 28 plus 3. And when you crunch it on out, you get 199. So f of 2 and f of 4 have opposite signs. So the intermediate value theorem does say there is a 0 in the open interval from 2 to 4. Again, we don't know what it is. All we know is that there is one. So again, for the intermediate value theorem to apply, f of a and f of b have to have opposite signs. If f of a and f of b have the same sign, both positive or both negative, the intermediate value theorem does not apply. That's the end of section 4.2.